Okay, so now we're going to tackle some properties of logarithms. So we're hitting SLL number 2, and we want to apply the product, quotient, and power properties of logarithms. Write a logarithm expression in expanded form and write a logarithm expression as a single logarithm. Very important here is remember, whenever you're taking a log of something, you're getting a power or an exponent as an answer. So a lot of the properties that we use for exponents are going to lead us to the properties for logarithms. The first property we need to talk about is the inverse property. Just remember that an inverse function undoes or reverses the operations of the original functions. If f inverse is the inverse function of f, both the following statements have to be true. When I do the composition in the direction, f inverse of f of x or f of f inverse of x, I should get x for all x in the domain of the inside function. Since log base b of x is the inverse function of b to the x, then the following has to be true. B to log base b of m has to be equal to m, composing a function with its inverse. Log base b of b to the r equals r, composing a log function with its inverse. So if I take log base 3 of 3 to pi, that should give me pi for an answer. 5 raised to log base 5 of e gives me e. Natural log of e to the rt is rt, just gives me exponent for the answer. 10 to the log of 5.8 gives me 5.8. Just composing a function with its inverse. Now in algebra, if m and n are two integers and a is a non-zero real number, then we have the following properties of exponents. A to the m times a to the n equals a to the m plus n. This is the product rule of exponents. When multiplying powers of the same base, add the exponents and keep the same base. We have the quotient rule. A to the m divided by a to the n equals a to the m minus n. When dividing powers of the same base, take the exponent in the numerator minus the exponent in the denominator and keep the same base. And then we have the power rule. When raising a power by a power, we multiply the exponents and keep the same base. So a to the m raised to the n equals a to the mn. Since logarithmics yield exponents as answer, if we take the logarithm of product, we get the same answer as taking the sum of the logs of each factor. If we take a log of a quotient, we get the same answer as taking the log of the numerator minus the log of the denominator, and so forth. So this leads to the following. M greater than or equals 0, n greater than 0, b greater than 0, and b not equal 1, and r being any real number. Then we have the product property. Log base b of m n equals log base b of m plus log base b of n. The log of a product is the sum of the logs of the factors. Quotient rule. Log base b of m over n equals log base b of m minus log base b of n. The log of a quotient is the log of the numerator minus the log of the denominator. And we have the power rule. Log base b of m to the r equals r times log base b of m. The log of a power is the exponent times the log of the base. And you can actually prove this by using your property of exponents. And I'll leave that as an exercise. We'll just kind of go through one really quickly. Use the idea that exponential functions are one-to-one. If m and m are greater than 0, there are unique numbers u and v such that m equals b to the u and n equals b to the v. And you apply the definition of logs. U equals log base b of m, v equals log base b of n. So if I do log base b of m times n, I'm going to substitute this in. Replace n by b to the u, replace n by b to the v. I add the exponents, and then I'm composing a function with its inverse. That just gives me u plus v. Remember, u was the log base b of m, v was log base b of n. So that shows you that the log of a product equals the sum of the log of each factors. And the proof for the quotient rule and the power rule work pretty much the same way. So let's turn to our workbook, and they just kind of give you a quick summary of those last three properties we talked about. And here we want to use the product property of logarithms to write the log as a sum and simplify. So for this first one, I have a factor of 2, a factor of x, and a factor of y. So I'm going to write this as a log of a sum. So this is equal to log of 2 plus log of x plus log of y. And that would be our answer. Let's take a look at this next one. So this would be log base 2 of 2 plus log base 2 of x plus log base 2 of y. Now you got to remember with this one, if I think of this as 2 to the first, I'm composing a function with its inverse. I'm just going to get 1 as an answer. So that's why they gave a little hint here, is recall that log base 2 of 2 is equal to 1. So I need to simplify that. If you write it this way in Alex, it's not going to say it's correct. So we're going to write that as 1 plus log base 2 of x plus log base 2 of y. And so that would be your answer. Let's try this one. So I've got a product of e, x, y, and z. So my factors are e, x, y, and z. So I'm going to separate each one of these out. This will be ln of e plus ln of x plus ln of y plus ln of z. Ln of e, though, think of this as an exponent of 1, composing a function with its inverse, that's just going to give me 1. And so that would be 1 plus ln of x plus ln of y plus ln of z. Now let's do some examples using the quotient rule. And again, I have to be on the lookout for anything that looks like this or looks like this, because I can simplify that further. So with quotient rule, it's the log of the numerator minus the log of the denominator. So it'd be log base 7 of z minus log base 7 of 12. Nothing to simplify there, so that's going to be my answer. Let's try this next one. This would be log base 7 of a minus log base 7 of 7. Here I'm composing a function with its inverse. So that's just going to become 1. So my answer is going to be log base 7 of a subtract 1. And here I'm going to put parentheses just to make it very clear that this a here is separate from the subtraction of 1. See if I can make that a look a little better. Let's try this next one. So I have log of 17 subtract. Now I have a x and a y. I'm going to separate those out. Each of them gets their own log. They're both going to be negative because they're both in the denominator. So just remember, if your factors are in the numerator, the log is going to be positive. If the factors are in the denominator, you're going to have a minus sign in front of the logs. And again, the book and Alex will rewrite this as log of 17 minus log of x minus log of y without the parentheses. All right, so now let's apply the power property of logarithms and simplify. So here my exponent is 5, so I'm going to bring that out in front. That's equal to 5 natural log of x. Here this is 5, so I'm going to bring that out in front. ln of e. ln of e, though, is 1. So that becomes 5 times 1, which is 5. And y'all may recognize that up here I'm composing a function to inverse. I should just begin an exponent of 5, but this is another way you can prove that. All right, let's try this next one. Now before I can pull that 2 in front, I need to separate the x from the r squared. So I'm going to rewrite this as log of x plus log of r squared. And now I can bring that 2 out in front. So I get log of x plus 2 log of r.